Good morning, residents. Today we're going to be looking at electrostatics. For those of you at home, we're going to be looking at calculations and the relationships. For those of you who are here, we're just going to do what we do. Okay? So we're talking about Coulomb's law. And last time that you were here, we spoke about how much Coulomb's law looks like Newton's law of universal gravitation. Okay? And when we were talking about it, we spoke about the relationships between the variables. So when it comes to Newton's law of universal gravitation, we're talking about masses, okay? But when we talk about Coulomb's law, we're talking about charge, okay? So, when we look at the relationships, what we need to realize is the following, that we have a proportionality type of relationship happening here. That means that the force is proportional to the product of the charges. In other words, when I multiply the two charges together, they are proportional to the force. That means when I increase the charges, the force increases as well. Okay? Also, we have the distance between the centers of the charges. Now keep in mind that the further away these charges are, the smaller the force will be. That should make perfect sense because remember, electrostatics is a non-contact force. And what that means is, the further away the things are, or the charges are, the smaller the force will be. That makes sense. Yes? Yes, sir. Remember that it's a squared relationship when it comes to the distance between the centers. Just the same as with Newton's law of universal gravitation, the distance between the centers of the masses was also squared in that relationship. Okay, I am drawing the similarities between the two for you so that there's less confusion. Realize that when you do an electrostatics question, you must say, am I dealing with charges? Am I using the right equation? When you do a Newton problem, you must say, am I dealing with masses? Am I using the right equation? Okay. Now, when it comes to this, in terms of the wording, we can say that the electrostatic force between two charged particles is directly proportional to the product of the charges on the particles and inversely proportional to the squared distance between those charges. That definition also looks very similar to your Newton's law of universal gravitation. Technically, you just have to study one set of wordings, okay, and swap out the variables involved. What do I mean by that? When we talk about Coulomb's law, we talk about two charged particles, and it's directly proportional to the charges between them and inversely proportional to the square of the distance. If we were using lug, we'd be talking about the two masses and the mass of the two bodies involved. So technically, you only need to study one definition and change the variables for these two particular calculations. Are we okay with that? Yes? Good. Now, I'll give you a chance to go back and write down. Let's just move through it. So, you did. Do you remember that when we talk about any kind of equation, if we want to drop the proportionality, then we need to introduce a constant sometimes. And that's because when we look at the relationship between charge and force and the distance between the charges squared and the force, we might not get a perfect relationship. So what scientists do is they plug in a constant value, and that constant value makes the relationship perfect. Okay? K is the constant that we use in electrostatics. And it's really important that you note that it's not the same value as G, big G, okay? So when it comes to K, it's actually 9 times 10 to the power of positive 9. It's a very big constant. That number is huge. 9 times 10 to the positive 9 is 9 with 9 zeros, okay? Which is very different to the other constant that we have for G. So just be very mindful of that. One of the most common mistakes is that we plug this in with a minus 9. Okay, must be positive. Then, F is obviously the electrostatic force. R squared is the distance between the centers of the charges as we know it. And then point charge 1 and point charge 2. So those are the two charges involved. it is important to note that in this calculation, we do not take into account the positive or negative sign of a charge. I'm going to say that again. We don't take into account the positive or negative sign of a charge. So if you get told that it's a negative charge or a positive charge, we just use the magnitude in this equation. Okay? And we figure out the force afterwards. What I mean by that is, if you were given one of these as negative and the other one as positive, at the end you would calculate the force and then say the force was attraction without using the pluses and minuses, because you know between the 2-point charges, if the one is negative and the one is positive, there will be attraction. If you are given two charges and they are both negative, for instance, you don't use that in the calculation, you just use the magnitude, and at the end you will say the force is calculated, but it's now going to be repulsion. Did that make sense? So please make a note of that next to this equation, that we don't substitute the sign in, only the value, and we make a call on whether it's attraction or repulsion based on the signs at the end.
Should I pause it?
That's fine. Are we good with that? Yes?
Can we write this down?
Okay. So repulsion is when the two charges are the same, and then of course attraction would be when the two charges would be opposite. Alright. Now what we're going to talk about now is we're going to talk about proportionality in terms of ratio and using the ratio. Using this equation, sorry, let me just go back to this equation. Using this equation with the numbers to plug and play is fairly simple. Okay? So usually you get given a question, you write a nice given list, and you can plug it into the equation, and it's fairly simple. And the only parts that are a little bit challenging might be that we're dealing with nanocoulombs or microcoulombs, and you have to remember what the actual conversion is. That might be the only thing that's challenging here. What we're going to focus on today is the proportionality, and we're going to use the same sort of style that we used when we were doing Newton's law of universal gravitation. Okay, so let's have a look at that. Can I move on? Yeah? Okay, so let's look at this style of question. This question says, two spheres with charges Q1 and Q2 is at a distance r from each other. The electrostatic force between the charge is F. What will happen if F is? So this is one of those things where we're changing variables, okay? Or we're changing the relationship between variables in terms of a ratio. We're not using numbers, okay? Does that make sense? We did ones like this previously for Newton's law of universal gravitation. And the rule is this. We're going to write down the formula, and we're going to sub in the values according to what we have. Will you pause for me?
Yes. Okay.
Okay. So for the first one, we're going to talk about what happens if Q1 becomes 3 times bigger. Okay. The first thing I'm going to do with these problems is I'm going to write the equation as is. So the equation says that F is equal to K Q1 Q2 over R squared. My rule is this. I'm going to plug the proportionality or the ratio into the equation and then bring it to the front. Yes? So F is equal to K. It's going to be 3Q1 Q2 over R squared. Make sense?
Mm-hmm.
Yes? Which means I have 3 times Q1 Q2 over R squared, which means that F will be 3 times bigger. Yes? That should make sense from a logic perspective. If one of the charges becomes 3 times bigger, then the force must be 3 times bigger because they're directly proportional. Okay? The only reason why we're using this method is because sometimes there's more than one variable that they shift, and you need some sort of mathematical way to make it make it work. Okay. Can I do the next one? The next one says that we're going to talk about two charges that are doubled. Okay. So both the charges are doubled. What are we going to do with it then? You are right. You're at the double. Alright, let's look at number 2. We're going to talk about both charges doubled. We're going to use exactly the same strategy as before. So we're going to write down the equation F is equal to K Q1 Q2 over R squared. The second question says both charges are doubled. That means I'm going to put a 2 in front of Q1. I'm going to put a 2 in front of Q2 over R squared. I'm then going to multiply the numbers together, bring them to the front of the equation so that I have my ratio or my relationship. So it's 4kq1 q2 over r squared, which means that it's therefore equal to 4f. Are we okay with that? It makes sense logically because if the relationship is direct proportion, we double the one, we double the other one, that means it's a factor of times 4. Yes? Yes. Okay, let's look at number 3. Number 3 is a little bit more complicated. It says charge 1 becomes 4 times smaller and the charge of Q2 doubles. Okay, so let's get that into the next equation. Ready? Yes.
Number 3 says
becomes
3 times bigger.
Oh, sorry, I missed one. Let's do 3. Ready? Right. So for number 3, we talk about the charge on Q1 gets 3 times, blah, blah, blah. We're going to do the same thing as we did before. Easy peasy, lemon squeezy. We're just going to plug it into the equation as we know it. Okay. So it says charge Q1 becomes 3 times bigger. So I've got K 3 times Q1. Charge Q2 becomes 4 times bigger. So 4Q2, and we have it over R squared. Yes? Good. Multiply, I'm going to do the maths and bring the number to the front, which means I get 12k q1 q2 over r squared, which means it's actually equal to 12f. 12 times bigger.
Okay.
You okay?
Yes.
Good.
So, man,
You have a question?
is it okay if you say F12? Like 12 F12?
You can say f times 12, but I prefer if you were going to write it down as an expression that it was 12f. Yes.
And you see, when you say 12k1, 12k q1, q2, can you 12 be like by the equal sign in that?
Yeah. So you can move the 12 to this point over here. Because it just means that it's 12 of those, pretty much. Okay? Because it's 12 times by the force. Right. Let's do the next one. We are now going to do the one that I was talking about earlier. We're going to do number 4. Let's do number 4. Ready?
Yes.
Almost? Camera needs a minute.
Okay, the minute is done.
Okay. Next one. I'm now going to talk about number 4. Again, I'm going to write the equation. K, Q1, Q2 over R squared. And now it's just about doing the maths. So we say Q1 becomes 4 times smaller. So I've got K and I've got a quarter Q1. Yes? 4 times smaller can mean that it's multiplied by a quarter. Yes? Or you can say Q1 divided by 4. Either way is fine. Okay. Which way would you like to do this mathematically?
Q1 divided by
You want to do Q1 divided by 4. And then, what's the second one? And then Q2 becomes 4 times bigger. Yes?
No, 2 sign. Number 4, man. Give number 3.
Sorry. 4 times smaller and doubles. So now we're going to get 2Q2 over R squared. Okay. Yes?
Yes.
I'm going to play with the maths. Are you ready?
Yes.
Okay. So I'm going to say K. I'm going to say a quarter Q1. So I'm going to pull it out. And I'm going to say 2 over 1 Q2. Yes? Mathematically, that is the same thing, agreed? Good stuff. Which means when I bring it forward, I'm going to have 2 over 4 k q1 q2 over r squared. Are you happy with that, guys?
Yes.
Which means effectively I have a half k q1 q2 over r squared. Which means that f is therefore half of what it was before. I like it. Do you like it?
Yes.
Good.
Okay.
Did you get it right? Did you try it? Let's do number 5. Hopefully I can read 5 properly and not try to do a whole bunch of other stuff. Ready?
I know, ma'am.
Okay. Come on, Cameron. You've got to be fast, fast, fast.
Yes, ma'am. Wow. You can erase it.
Good. Number 5 says the distance between the spheres becomes 3 times smaller. So now, again, I'm going to start off with my equation, but now the maths is a little bit more tricky. So, f k q1 q2 over r squared, and I have the spheres are now, the distance between them is 3 times smaller. So I'm going to plug in a, what's it called? Fraction. 3 times smaller would mean that it is multiplied by a third. Do you agree?
Yes.
So it's now a third of r. Yes? My problem here is that the value for r needs to be squared, which means this whole thing must be squared. And that is a very important part of this. Because although we're squaring r, we also have to square the ratio that's involved. That means I end up with k q1 q2 over r squared, and that r squared is over 9. Would you agree? Yes? Because it's 9 times smaller. Actually, I think I'm going to do this instead. I'm going to say 1 over 9 r squared. So I multiply the 2 in, and it'll be 1 over 9 and r squared. I'm now going to take the 1 over 9 and bring it into the numerator of this particular fraction. And the rules are simple. If I'm going to move it from the bottom of the fraction to the top of the fraction, I have to flip it around. Okay? Yes?
Yes.
So what I do is I tip in times. You've heard that expression before? I take it from the bottom here, it becomes 9 over 1 times by kq1 q2 over r squared, which means that f is now equal to 9 times what it was before. Do you see that?
Yes.
Are you sure?
Yes.
Mathematically, are we okay?
Yes.
Logically, are we okay?
Yes.
The reason why I'm asking about the logic is because these two spheres, these two things that are charged, have now gotten closer. Are you expecting the force to be bigger or smaller?
Bigger.
Bigger, because they're closer together. Yes?
So
Yes.
the more distance, and
There's
it
less
becomes
distance
smaller.
between them. So the smaller the distance, the bigger the force. The bigger the distance, the smaller the force. It's important to take that into account when we're doing this kind of problem. Okay, make sure you've written it down nicely for me. Our next question asks us to look at what will happen if the distance between the spheres becomes 3 times bigger. Okay, so now if we increase the distance, what happens now? Okay, we're obviously going to have a smaller force. Okay, you done? Let's look at the next one. So we're going to say f k q1 q2 over r squared, and now it becomes 3r, and 3r squared. Again, notice that the 3 is connected to r, but I still have to square the whole thing. I can't just square the r by itself, okay? Which is why I then end up with k q1 q2 over 9r squared. Yes? I've got this at the bottom of my fraction. To move it upwards, again I'm going to tip and times. Agreed? This 9 is a whole number, it's not a fraction, which means when I bring it to the front, tip and times it, I'm going to end up with 1 over 9, my bad, 1 over 9 times 5, k, q1, q2 over r squared, which means that I have 1/9 of force. This makes sense mathematically, but also logically. If the distance is bigger between the two objects, that means that my force will be smaller. Remember, it's a square factor, so because it's 3 times the distance away, we've got 9 times the force. Okay? And we're ready to do the last one for proportionality. The last one for proportionality is number 7, and it's got the combination of what happens with the charge as well as what happens with the distance between the centers. Remember, this is just a tool to help you when the numbers are a little bit too complicated. So sometimes, like up until about number 4, 5, you can do that in your head and you can say, this is the relationship, this is what will happen. But when they move both things at the same time, it becomes a little bit more challenging. So let's look at number 7. And for number 7, it says the charge on Q1 becomes 4 times bigger, the charge on Q2 doubles, and the distance between the spheres halves. So I'm going to write down the equation, and then I am going to talk about what's happening with each variable. Tell me what happens with Q1?
4 times.
So I'm going to say 4 times Q1. Are we okay with that? What happens with Q2? Double. So 2 times Q2. What happens to R?
Halves.
It halves. So I'm going to have a half times by R. Notice that I'm going to put it in brackets again, just for safety's sake in terms of the maths. Alright, now I'm going to bring all the numbers to the front so I can get a whole idea of what's happening. That means I have 8 k q1 q2 over 1 over 4 r squared. Do you agree? I'm now going to do that tip and times thing. Are you ready for it? I have 8 over 1. I'm writing it like that because I'm going to need to use something fraction-wise. Times by, if I tip and times to bring that up, it's going to be 4 over 1. Agreed? K, Q1, Q2 over R squared. That gives me 8 times 4, which is how much? 32. I have 32 F. Do you see it? Yes? And this is where using the equation becomes really, really handy. Okay.
Okay.
We can stop for now. Okay, so for the second part of this, we're focusing on how to actually use this particular equation. The rules are really simple. They're the same rules as we've been using for ages now. When you get a calculation like this, one of the most important tools that we're going to use is a given list. So you're going to write down, okay? You're going to write down whatever's been given to you, and we're going to make sure that the units are good as well, okay? Particularly in this one, charge is never actually measured in coulombs straight. It's usually measured in a, what's it called? In a variation of the coulomb, or in a power of the coulomb, or in a fraction of the coulomb. So we're talking about nano, micro, milli, okay? Pico as well. Which means those are conversions that you will need to be completely happy with using. Yes?
Okay.
So we're going to work from our textbook now. You're going to be doing 2 of the examples from your textbook. I'm just trying to check which page we're on. Anybody? Aha. Alright, we're going to be talking about On page 109, nope, I'm lying to you. Don't like lying to you, Brad. I like being super honest. There we go. On page 106 and 107, that is the bit about the charges. I want you to have a look at that. I want you to create your note, or I want you to make sure that your note is a little bit fuller using page 106 and 107. We're going to do the example from the textbook there on the bottom of page 106, and then we're going to be working with exercise 6.1 on Coulomb's law. All right. Thank you, Chloe. You can pause. Goodbye, guys.